Have you ever wondered what makes certain electronic components switch off reliably and stay off, even in dynamic power systems? The ability to precisely control when a component stops conducting is crucial for safe and efficient operation. This is especially true for silicon-controlled rectifiers, or SCRs, which are vital in many power control applications. If the SCR turn-off time is insufficient, the device will fail to block forward voltage and will re-trigger, or turn on again, even without a gate pulse. This phenomenon is known as commutation failure, and it leads to a complete loss of control over the circuit, often resulting in short circuits, component damage, or system malfunction. The core reason behind this is the internal physics of the SCR. When an SCR conducts, charge carriers, specifically electrons and holes, flood the semiconductor layers. To turn off, these charge carriers must recombine or be swept away, allowing the depletion regions to reform and the device to regain its forward blocking capability. This takes a finite amount of time, known as the reverse recovery time and then the gate recovery time, which together constitute the SCR's turn-off time, often denoted as TQ if the external circuit applies a reverse voltage for a duration shorter than this internal TQ. The SCR simply will not be ready to block the forward voltage again and will conduct prematurely. To prevent this, designers must ensure that the circuit turn-off time, or TC, which is the duration for which a reverse voltage is applied across the SCR, is always greater than the device's specified turn-off time, TQ. This is achieved through careful design of commutation circuits, which are responsible for momentarily reducing the anode current below the holding current and applying a reverse voltage. Common methods include forced commutation, using external components like capacitors and inductors to divert current, or natural commutation, where the AC supply naturally provides the reverse voltage during the negative half cycle. A crucial insight for power electronics is understanding that TQ is not a fixed constant. It is influenced by factors such as the peak forward current before turn-off, the rate of change of reverse current, and the junction temperature. A higher junction temperature, for instance, can increase TQ, making it even more challenging to ensure proper turn-off. Device manufacturers specify TQ under worst-case conditions to guide engineers in designing robust power converters and motor drives, where reliable switching is paramount. Ultimately, ensuring sufficient SCR turn-off time is about maintaining absolute control over power flow. By diligently designing circuits where the externally imposed reverse voltage duration exceeds the SCR's internal charge carrier recombination time, engineers guarantee predictable switching behavior. This foundational principle prevents catastrophic commutation failures, ensuring the efficiency, safety, and longevity of power electronic systems, from industrial motor controls to high-voltage DC transmission.